Okay, and so this from 3 to 2, this is H alpha, the red line. From 4 to 2, this is that teal line. This is H beta. And then from 5 to 2, this is H alpha beta gamma. And then this one is the delta. Okay, so those are the only visible part of the spectrum for hydrogen at all. Okay, and so let's go in and let me write down Bohr's assumptions. So the first assumption that he had was that there are stable allowed orbitals. We'll do it the other way. Okay. And what goes along with that is that if an electron is in a stable orbital, it does not radiate, even if it is accelerating. Okay. And then 3, we have that if an electron transitions from one stable orbital to another, it will emit, or if it goes from higher to lower, it's going to emit, and if it goes from lower to higher, it will absorb. It'll emit or absorb a photon with energy equal to the energy difference between the stable orbitals. Okay. And so now what we can do is we can go in and kind of take a look at the development for the Bohr model of the atoms. If we had tons of extra time, I would actually probably have gone through this, by hand in the lecture, because it's one of my most favorite calculations. And the reason for that, especially in this class, is because everything you've already learned everything you need to know in order to follow what Bohr did. You can do this. Okay, we have enough physics behind us to be able to follow and understand everything that was done. And so this does not need to be, here's your equations, let's use them. We can actually derive this. But we'll go ahead and just kind of skim over it, because I don't need you to be able to do the derivation. That's not the important bit. I need you to understand how it came about, and these are the results. And so that's what I want us to see. So for the Bohr atom, we have our positive charges and the neutrons in the nucleus. They didn't know there were neutrons at that time, but we're going to put them in anyways. And so Z is your atomic number. It's the number of protons in the nucleus. It indicates which element the atom is. And then here's our electron. Now, this is the thing about the Bohr model, is that it correctly describes atoms with only one electron. If you have more than one electron, then this is all wrong. It does not work. So we need single electron atoms. And so if they have more protons, then you need to ionize the atoms so that they only have one electron. And that'll make it hydrogen-like or Bohr kind of thing. So here's our electron. The charge is minus E. And therefore, we're going to have an attractive force on the electron, causing it to, move in our circular orbit. Here's the magnitude of the electric force given by Coulomb's law, KQQ over R squared. The charge in the nucleus is ZE. The charge on the electron is minus E, and we're at this distance R squared. So this is the result we get. So that's our force. Since it's moving in a circle, we would say that the net force in the centripetal direction is ma centripetal. That force is the electric force, and the centripetal acceleration is v squared over r. And so then with this, we can then cancel this r with that r there. Oh, this is in the lecture handouts, by the way. I forgot to mention that. And so mv squared is very nearly 1/2 mv squared, which is our kinetic energy. Okay. And so what you get is that mv squared is k times z times e squared over r. And so 1/2 of that's 1/2 of kz e squared over r. And if we look at mechanical energy, you get that the mechanical energy is the kinetic plus the potential. This is the electric potential. And so you have your kinetic energy 1/2 mv squared. The potential energy is q times the electric potential due to the charges in the nucleus. Okay. And so then this is our 1/2 mv squared, the kinetic energy, and we get this as minus E for the charge of the electron, kq over r for the, the electric potential for the charges in the nucleus. And so we get this is 1/2 mv squared minus kz e squared over r. And if you plug in that the kinetic energy here goes into there, then we can simplify this energy down into this value here, which is negative 1/2 kz e squared over r. Okay, because we get this half kz e squared over r minus kz e squared over r. And so half minus 1 is minus 1/2. And so what you want to note is that the mechanical energy for the electron as it orbits the nucleus in an atom is negative. And what this tells us is that the electron is bound, so that you have to add energy to the electron to remove it from the nucleus. Okay, so this is, essentially indicates that the electron is bound. Okay. And so Bohr went in and he made a quantization condition, kind of very similar to what Planck did in order to resolve the black body radiation problem, the ultraviolet catastrophe issue, right? And what he stated was not that the energy had to be quantized, certain discrete values, but that the angular momentum had to be quantized. And then if you asked him why the angular momentum had to be quantized, he's like, I don't know, this is what works, and so he kind of knew where he needed to get, and this was the assumption that needed to be made. And so he had no real defense for why the angular momentum was quantized here versus the energy was quantized there in the black body case. So I was trying to remind you all of what the angular momentum was. It's the rotational counterpart to the momentum, the linear momentum, which was the mass times the velocity. And so m becomes I, v becomes omega. And so you could look at it as I omega. You could also rearrange this so that it becomes m times v times r. Okay. And so his angular momentum, m times v times r, is an integer times Planck's constant over 2 pi. So very often they'll do this h over 2 pi value. They'll refer to this as Planck's reduced constant, and they write it as h bar. So they bar the h. So, well, actually they slash the upper stem on the h is what they do. It's not really barred, but they call it h bar. So what am I going to tell you? So you get an integer times this constant is our angular momentum. And then from that, we could solve for the speed in the nth allowed orbital. And then if we go in and look at that, we can rearrange this to get a result for the radius of the nth allowed orbital. Okay. And so by plugging this in and solving for r, we get that it is n squared over z. So this integer value for the angular momentum from the quantization condition divided by z, which is the number of protons in the nucleus, times Planck's constant squared over 4 pi squared Coulomb's constant times the charge of the electron squared times the mass of the electron. So a bunch of fundamental constants. This combination of values is referred to as Bohr's radius, and they usually write that as an A0, an A naught. And this is that, 0.0529 nanometers. Okay. And so now that we have the result for the radius of the allowed orbitals, and you just let the n value label out which orbital it is, they'll n equals 1, 2, 3, 4, so on and so forth. You could go in and take a look at your energy, which was that minus, because it's bound, 1/2 kz e squared over r, plug in this for r, rearrange it a little bit, and what you get is this result here. Okay. And so you get that the energy of the nth allowed orbitals is minus, and then this bunch of constants, 2 times pi squared times Coulomb's constant squared times the fundamental unit of charge to the 4th power times the mass of the electron divided by Planck's constant squared. This has a numeric value of 13.6 eV when you plug it all in. And then it's times z squared, which is the number of protons in the nucleus, squared over n squared, which is our integer for the quantization of the angular momentum, this n right here. Okay. And that's known as the principal quantum number. That's what that is. And so then if you look at the transitions, so the energy of the photon was the energy difference between allowed orbital states. And if we plug in our energies and we rearrange things, then we get this result for this energy difference. And since the energy difference was the energy of our photon, which is hf or hc on lambda, then we can solve for 1 over lambda is our energy difference over hc, gives us this bunch of constants times z squared times our 1 over the n final squared minus 1 over n initial squared. And then you're like, oh, and then we will look at this constant, which is 2 times pi squared times Coulomb's constant squared times the fundamental unit of charge to the 4th power times the mass of the electron divided by Planck's constant cubed divided by the speed of an electromagnetic wave in a vacuum. What you get is Rydberg's constant. So Bohr derived Rydberg's constant. And then people went, oh, this must be right, because it seemed like it was just all out in left field doing random whatever things. And then all of a sudden he derived a constant that we knew from experiment. So Rydberg's constant was given empirically. By doing repeated experiments, we found this value. Bohr derived it. And so this is a big deal for the Bohr model itself. And so this is what Bohr was able to do. Let me write down the key results. And the key results are the radius of the allowed orbitals and the energy of the allowed orbitals. Okay. So the radius of the nth orbital is this, n squared on z times the Bohr radius, where the Bohr radius is 0.0529 nanometers. And then the energy of the allowed stable orbitals is minus 13.6 EVs times z squared over n squared, where again, n is any integer, 1, 2, 3, blah, blah, blah. Okay.